Let's talk about similar figures again. This is the first part of lesson 11.2. So back to our definition for similar polygons. Similar polygons are polygons in which corresponding angles are congruent and corresponding side length are proportional. So triangle ABC is similar to triangle DEF, and that is because angle A is congruent to corresponding angle D, angle B is congruent to corresponding angle E, and angle C is congruent to corresponding angle F, and all their sides have the same similarity ratio. AB compares to DE, BC compares to EF, and CA compares to FD. Remember, CPC, TC, corresponding parts of congruent triangles are congruent? Well, with similar polygons, we can use some abbreviations also. So, we can use CAS, TC, which means corresponding angles of similar triangles are congruent, and CSS, TP, corresponding sides of similar triangles are proportional. These would be used when you're doing proofs to shorten the explanations. Let's apply some of what we've learned to show that triangles are similar. Using the definition, you have to show 3 pairs of corresponding angles are congruent, and the ratios of the corresponding sides are all equal. You can use postulate AA, where we know that if we have 2 angles of corresponding polygons that are congruent, then, corresponding triangles are congruent, then we know that all 3 will be congruent. So even though we've been looking at 3 pairs being congruent with the angles, we can actually get away with 2 pairs. The AA similarity postulate. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the 2 angles are similar. So this is the same as saying AAA, which is all the 3 angles, to prove similarity, or to use the former postulate we knew where it was AA would cover AAA. And so now this is the updated postulate, and it's a little bit shorter than what we had before. So if all we have to do now is prove 2 sets of angles, corresponding sets of angles in the triangles congruent. So angle A is congruent to angle X, angle B is congruent to angle Y. Example 1. Can the AA postulate be used to prove that each pair of triangles are similar? And we have these various pictures. They're both the same picture, but we're using different things in the pictures to prove. So let's take it a step at a time. And we can prove that, let me see if I can get this to work today. We can prove that angle D is congruent to angle H, and we can prove that angle E is congruent to angle G. Now we can do this because we have a set of parallel lines, and these angles, the corresponding angles that we just proved, are alternate interior angles. So this means now that triangle DEF is congruent to triangle HGF, and yes, that means that they would be similar. Moving on, in example 1, we now take the same drawing, but with this drawing the only information we have is that we have right angles. So we have this right angle that's placed here means that these two angles are also right angles, and so is angle X. So we know that WXV is congruent to YXZ because they are both 90-degree or right angles. However, we don't have any information on our other angles, so we cannot prove this similar. We have to have two corresponding sets of angles to prove similarity. And can we prove that a right triangle with a 35-degree angle and a second right triangle with a 55-degree angle is similar? So here are the two triangles. First of all, we know that both of these angles are right angles, so they are congruent. And we have an angle of 55 here. We have a 35-degree angle here. However, if we say that 90 minus 35 equals 55, these two triangles could be similar. Because 35 and 55 equal 90, they would complete the measurement of the triangles, and so, yes, we can prove them to be similar. Theorem 11.2.1, we've just done AA postulate, but now we can move to side-side-side similarity theorem. Now this is very much the same as side-side-side congruence, with the exception of, even though the angles are congruent, the side lengths are different sizes. So to prove this and to use this theorem, what we can do is set up our proportions of the sides. And we have side AB, and let me get my handy pen here. Side AB is congruent to side XY. BC is congruent to YZ. And AC is congruent to XZ. So, we can, even though we don't know the angle measures, we can prove these triangles are similar according to the similarity ratio in the triangles, and we can state that they are similar. So triangle ABC is similar to triangle XYZ. Now in theorem 11.2.2, we'll use side, side, side instead of, side angle side instead of side, side, side. And the angle has to be an angle included in between the sides that we're proving. So if we take, and let's just take this set of triangles here, and this is an option you always have, is to make extend lines to create another triangle. We can say that this whole line here, dx, is congruent to xy. So the whole line, dx, would be congruent to xy. And this whole line, de, would be congruent to yz. So now you have two sides that are congruent, and the angle in between, angle 3 and angle 1, are congruent. And how do we know that? Well, we drew sets of parallel lines, and these are corresponding congruent angles. So we can now state that angle XYZ is similar to angle XDE. In example 2, if the triangles can be proved similar with the given information, we'll write a similarity statement and name the postulate or theorem that justifies it. So let's look at A of example 2. We have two triangles, And by just looking at them, it's very hard to tell if they're similar. We do know that they have two angles that kind of look like they're 90 degrees, but we can't count on it. But, however, we do have sides for both triangles. We have the side lengths. So let's take the longest and the shortest and compare them, and then put in the remaining sides and see if we have a consistent ratio. So we take the larger triangle and we set a proportion that is 20 to 15. And 20 over 15 would then be compared to 12 over 9. And we use the last or third side, and we have 16 over 12. And each one of these reduces to 4/3. So it is constant. The similarity ratio is 4/3 for all of the sides. So we've just proved these two triangles congruent by side-side-side similarity theorem. Now let's look at this figure. We have two triangles. We have some shared angles. We have vertical angles that are shared. But we do have two side lengths on each. So let's see what we can do. We don't have 3 side lengths, and we don't have any more angles. So we can compare 15 to 10, 15 over 10, and 12 over 8, 12 over 8. They both are have a similarity ratio of 3 seconds. And angle JLK and angle NLM are congruent. However, they're not the included angle. The two angles we just discussed are not the included angle. So let me show you that. For this to work, see, right now we have this set of angles, but we have these sides that we're comparing. So for this to work, we'd have to have the angle at K, and we'd have to have the angle, the measure of the angle at M. So we cannot prove that these triangles are similar. And the last one, we're going to take a look at the smaller triangle. We have T, U, and V. And then we have a larger triangle, which is the whole side, and it's S and U and W. So we have a larger triangle and the smaller triangle. Angle U is congruent to itself. So angle U is congruent to angle U by reflexive property. Now let's set up our ratios and see if they work. We have 6 over we have the small triangle to the large triangle, so it would be 6 over 6 plus 4, which is 10. So 6 over 10, and on the other side we do the same thing. We have the smaller triangle 9 over the total of the whole side, which is 15. And 6 over 10 equals 9 over 15 is 3/5. And that is consistent between both of those side ratios. And we also have a shared angle. So, and the shared angle is in between those sides, right here, or included in the sides. So we can say, yes, this is a set of similar triangles by side angle side. So let's take a look at a couple of additional exercises. Are these similar triangles, and what is the ratio? So we have numbers. The numbers aren't always set up perfectly, so sometimes you have to sort them out. I listed these 3 larger numbers on the top, 15, 24, and 21, and then I took a look at the smaller numbers to see if there was something similar, and actually there is, except that I wrote one of the wrong angles here. There we go. Okay, so 15 is to 5 as 24 is to 8 as 21 is to 7. If you divide each one of those fractions, or you simplify the fractions, I should say, their similarity ratio is 3. So they are similar triangles. Here's another set, and I've placed the smaller numbers on the top, and you have the option to do this unless they tell you otherwise, unless you have a word problem that tells you that the larger ones have to be on top. So 6, 12, and 16, and then I took a look at the ratios on the bottom, for the bottom, and I realized that 6 over 9, which reduces to 2/3, is the same as 12 over 18, which reduces to 2/3, which is the same as 16 over 24, which reduces to 2/3. Now, if you'd put the larger this other set of numbers on top and actually inverted all of these, your similarity ratio would be 3 seconds. And if they don't specify, either answer is correct. Here's another exercise. We have 2 triangles. This is a parallelogram, and it has 1 diagonal. Now, if you remember anything about your parallelograms, you should remember that these alternate angles are congruent, and A and C are also congruent to each other. And when you divide with a diagonal, that you'll have 2 sets of congruent triangles. Right off of the top, you could say that these triangles will be similar because they are congruent. However, if you have to prove it, you would have to write out ratios or prove the angles were similar, so forth. The important thing to know is, because this is a parallelogram, DC is parallel to AB, AD is parallel to BC, and you could use alternate interior angles to prove, or you could use the properties of your parallelogram to prove. But in actuality, when you have a figure like this, it not only justifies the AA similarity theorem, but also side angle side or side side side. Another set of triangles. Now these triangles, they look similar at first. If 6 divided by 3 would be 2, 6 divided by 3 would be 2, 4 divided by 2 would be 2, so they have the same ratios. However, the markings on the angles tell us that these angles are not the same measure, and so we cannot state that these isosceles triangles are similar. So your homework for 11.2a is numbers 1 through 6 and 7 through 9. Be sure to contact me if you have any difficulties, and we'll work on some of these similar problems tomorrow.